Very good evening to friends in India and Asia region, and good afternoon to friends in Europe, and good morning to our speaker and other colleagues from US. I think we have a couple of other audience also from US. I see that. So really, it's nice that today we have Professor Kerem Camsari from University of California, Santa Barbara, to give his talk. So on behalf of my team, co-convener Dr. Rajbhushan Singh. So we really express our gratitude to Kerem for joining this and other participants as well. Because of you, this webinar series is going well. So I think you know him, but as a matter of formality, I will give a very brief introduction about him. So Kerem Camsari is an assistant professor of electrical and computer engineering at the University of California, Santa Barbara. He had received his PhD in electrical and computer engineering from Purdue University in 2015, where he continued on as a postdoctoral researcher between 2015 and 2020, before joining the Department of Electrical and Computer Engineering in UC Santa Barbara in 2020. His PhD work established a modular approach to connect a growing set of emerging materials and phenomena to circuits and systems, a framework that has also been adopted by others. In his postdoctoral work, he used this approach to establish the concept of P-bits and P-circuits as a bridge between classical and quantum circuits to design efficient, domain-specific hardware accelerators in the Baron-Moore era of electronics. He has received the IEEE Magnetic Society Early Career Award for this work. So I think this is very brief, and for the participants, I request that we take the questions at the end of the lecture. So during the lecture, if you have anything, you can write always in the chat box and we will take it after the lecture. So with this, thank you so much, Kerem, for joining so early. It's all yours. Looking forward to a lecture. Thank you.
Well, thank you very much, Shubhankar, for the nice introduction and for the invitation for this famous seminar series. It's really a privilege to be here. And today I want to tell you a little bit about this work we've been doing for some number of years now, and it's this work on probabilistic computing. And I'd like to give a brief introduction and what this is, because Shubhankar told me to kind of make it generally accessible in the beginning. So I made some slight changes. So I plan to give a 40-45 minute talk. Please let me know if that's okay, and we can go from there.
Yes.
All right. So very good. Thank you. So let me start by saying a few words on where computing today is. And we have, of course, we're all familiar with the amazing bits, which are deterministic. They're all 0 and 1, and we do all our information processing with bits. And these bits are represented by our transistors. You all know this, our amazing revolutionary technology. We have CPUs. Now you hear about GPUs and TPUs, these accelerators and domain-specific ideas with billions and billions of transistors. The technology is at this amazing transformative stage. And on the maybe on some other end of a spectrum, you've heard about the qubits, which are, even to describe it, you need this technical term. You have to use this technical term, this superposition. It kind of means that an object like a qubit can be 0 and 1 at the same time, although this doesn't do justice to exactly what's going on, and it would take us too far afield to get into the subtleties of that. But the reality of today's computing is you have these major players like Google, Santa Barbara collaboration, the IBM, D-Wave, IonQ, all sorts of efforts to build these quantum computers. And for reasons that we're not going to get into, it's very difficult. It's a tremendous engineering challenge to build these large-scale quantum computers. Now, if you look at these two things, they kind of look irrelevant and unrelated, but I'd like to argue that they are both domain specific. Now, what does that mean? Domain specific means that these amazing computers in bits and qubits are not going to solve everything and are not going to make all of your computation better, just like the old days where, you know, you bought a computer and then 18 months later it was out of date. These days, it's more about solving some problem a little bit better. In the case of bits, this is machine learning. In fact, GPUs and TPUs are very good at solving a specific thing, namely matrix multiplication, and not necessarily better for everything in terms of general purpose computation. So quantum computing is also a little bit like that quantum computers are not expected to make everything better, but really niche problems like solving quantum chemistry or simulating quantum physics itself. So this seems to be the future of computing, where it means a more heterogeneous landscape, and it means more creativity is expected from all of us. So it's a good era to be in. Now, this probabilistic or p-bits are also domain specific, and they've got, I'll show you that they have connections, very strong connections to statistical machine learning models, statistical mechanics-based machine learning models, and also they share a lot of applications with this noisy intermediate scale quantum era. It's this era of quantum computing where we don't have this very large scale fault tolerant quantum computers. So what is a p-bit? You know, again, to trade an unknown with a couple of other unknowns, a p-bit is a binary stochastic neuron. Well, what is a binary stochastic neuron? A binary stochastic neuron, or a BSN, is this object where you have an analog input and a digital output. Okay, so the digital output can always be 0 or 1, or let's say -1 and +1, and your analog input sort of can be any analog number in the real number range. And the device behavior as a function of this analog input is something like this: that if you come in with an analog input of 0, then your device shows random telegraphing noise, that it's either 0 or 1 with 50-50 probability, but most importantly, it is not periodic. And if you change the analog input to +1 or -1, you sort of change the duty cycle of this bit stream while still keeping it random. Okay, so this is the basic device operation, at least in a very abstracted manner. And if you sweep the input from -4 to +4 and slowly look at your output, then you would see something like the blue trace here. And if you take the average, you would see something like a sigmoidal, a graceful change of the probability of the output. And sometimes we write it mathematically like this. We say that, okay, I'm taking the sign of a random number compared to the hyperbolic tangent function. And that really that shouldn't be complicated. That really reproduces the blue trace or these bottom figures in a very simple way. Okay, so that's the p-bit. But then how do you make a p-computer? How do you actually compute anything with this? So this is the behavioral model we discussed, but then you need to build a computer, and for that you need at least some number of p-bits that are interconnected. And the way it works is you take n of these p-bits, each having an input and an output, and you collect the output, pass it through this interconnection matrix, sometimes called the synapse, a sort of a bad term borrowed from biology into machine learning. This has nothing to do with your real synapse in your brains, but it's an interconnection or a synapse network that sort of collects these outputs, calculates an input for each p-bit, and then routes it back to the p-bits. So this is a recurrent or a feedback network where it goes round and round as a function of time, as a dynamical system, and this network reaches some probability distribution. Now, there are a couple of things that we need to talk about here. This is the architecture, and this is it. All the problems, everything I'm going to show really is based on these two building blocks, and then the question of how we build these things efficiently. Now, this is clockless. What that means is if you're familiar with computer architecture and computers, everything in your computer is based on a clock. It is based on a global clock that works like a traffic light. But in p-bits, being inspired by nature a little bit, where nothing is clocked, everything is happening at the same time, this architecture sort of takes inspiration from that. It is clockless. There is no clock that sort of regulates which p-bit fires and which p-bit doesn't. And that leads to a very important conclusion, in fact, an observation, that this becomes massively parallel. It becomes measurably better if you put more and more p-bits because you're increasing the parallelism in the system. Now, there is an important caveat here, which I'm not going to talk about in great detail, but what that means is when you have an asynchronous system like this, there are two time constants, which is your p-bit time and your synapse time, and your p-bit time needs to be slow compared to your synapse time. Or in other words, your messenger, your interconnector needs to act fast. Because if imagine a situation like two p-bits connected, if I flip, and before that information goes to the next pivot, I flip again, then it doesn't quite work. So this is kind of a detail that you have to worry about in hardware implementations. So what do I do with this? What are the kind of applications with p-bits? Well, there's a very wide application space that you can demarcate into two groups, and they are optimization and sampling problems. Now, those are technical, but if you want to bring it to the real world, you can say one of them is more quantum inspired, where traditionally quantum computers have been focused on solving optimization problems. And the other is machine learning and AI inspired, where there's a lot of probability sampling and learning probability distributions and so on. Now, there's something that we invented, this thing that's called invertible logic, which is this very interesting concept of running circuits in backwards. Now, you're all familiar with the digital VLSI technique of building a multiplier, okay? So how do you build a multiplier? Well, you all know the school book algorithm. You write AND gates and full adders. I'll show you an example later, and it multiplies two numbers in digital logic. But if you do it with P circuits, you can run it in reverse. You can ask the circuit a question of saying, what makes this output 6? So this is also known as, and then the circuit will tell you what makes the output 6. It'll find the factors for your circuit. It doesn't make the factorization problem easier. This is sometimes confused. Factorization is a problem that is believed to be in NP, which means that there is not going to be any shortcuts with classical or probabilistic computers, but it makes the overall thing much faster. There's a lot of advantage still, even if that conclusion is still true. I'll show you an example of this. And then there's this whole big family of combinatorial optimization problems, like the traveling salesman problem, the problem where you ask, okay, there's 1,000 cities in the state of California. How do I visit each state exactly once while minimizing my distance? So this is, by the way, this takes around 15,000 miles approximately. This is not solved exactly. This is, again, this is one of those problems where in order to be sure, you need to be solve this enormous amount of combinations. This is another problem that is in NP. In fact, this one is NP complete. So these problems don't have shortcuts, but our argument will be that if you use p-bits to solve problems like this, you can get a lot of prefactor advantages and a lot of speed up. And more intriguingly, we have this work on quantum emulation, that it turns out that in condensed matter physics, it's been known for a while that certain quantum systems can be efficiently emulated by probabilistic systems. Okay, so this idea did not come from us, but we've taken that software algorithmic idea and argued that, hey, you can take a quantum system like the D-Waves annealer and build replicas of p-bits using this condensed matter technique I just mentioned and solve quantum problems. And I'll show a quick example of this as well. And we believe that the room temperature operation and fairly easy scalability of p-bits compared to qubits, of course, is a major advantage in this domain. Now, what I'm not going to talk a whole lot about is these Bayesian networks and Boltzmann machines, which are major areas in machine learning. I'll just say that whenever you have a probabilistic building block in your algorithm, p-bits look like a very good fit for that application. All right, so how do you build a p-bit in hardware? Well, there's probably 1,000 answers to this question, but I'm going to show you one specific way based on magnetism, because that really gives you a big advantage if you look at the physics of magnetism. Now, if you're not familiar with a magnet is an object, in the toyest models of all. If you have two states, a red state and a blue state, and you try to separate these two states by an energy barrier. And if you talk to magneticians, they'll say, hey, we try to make this barrier as large as possible because with the retention time, the noise that there's noise that heats these balls up from the bottom and they can jump over the barrier. And in magnetism, of course, non-volatility is sacred, that you want your state to be in that state forever. And the magneticians will tell you that, look, this is this exponential behavior. If there's a prefactor that's material dependent, that's like picoseconds to nanoseconds. And if you put 40 to 60 to this formula, you'll get some number of years in retention. And that's great, because it means that your fridge magnet is not going to lose its memory for the next 10 years, or your iPad will, or your hard drive will remember its memory in the next 10, 15 years. But if you take that formula seriously and reduce KT to the energy barrier to around a KT or so, something interesting happens, that the same formula now tells you that you're going to be jumping up and down between these two states with picoseconds to nanoseconds ratios. And this formula isn't quite true when you reduce the barrier so low for technical reasons, but this gives you the idea. Now, a device in our field that you may be familiar is this device that's called magnetic tunnel junction. And a magnetic tunnel junction takes two such magnets, separates them by a barrier, and this remarkable piece of transport physics, that if these magnets are pointing in the opposite directions, you get a high resistance, and if the magnets point in the same direction, you get a low resistance. And this resistance ratio is around 2 or 3. Now, people use this for memory applications all the time. But if you use one of these unstable magnets, low barrier magnets that I described for the MTJ, you see something like this. As a function of time, you have a resistance that's fluctuating up and down as a function of time. And this can be picoseconds to nanoseconds, depending on your magnet design. Now, this statement that I'm making was a theoretical statement that we had been making, and we had been receiving some criticism on this. No, magnets can never be picosecond to nanosecond, and people were writing papers about this. But then, this was really a theoretical prediction just until a few years ago. And it started with our interest in this field, and we collaborated with Tohoku University, Professor Shunsuke Fukami and Professor Hideo Ono. They're, of course, these world experts on controlling these magnets. And the first thing they did was to give us these stochastic MTJs whose resistance changes as a function of time. And this is the most curious thing. You go to the lab, this is a 2-terminal resistor, you put your scope on it, you look at the resistance, you're not doing anything to the object. It's changing from 10 kilo ohms to 20 kilo ohms as a function of time. It's quite amazing, actually. But the first thing they gave us was around, you can see the time scales here, 100 seconds, 50 seconds, 1 second, nowhere near the picosecond that I've been talking about. But then there has been recent developments. First, IBM came earlier this year, showed that these stochastic magnetic tunnel junctions can function at nanosecond operations. And then Tohoku came a few months later, another experiment showing essentially the same thing. And using their ideas, we've improved our p-bit implementation. Now we think MTJs with no fixed layers at all, both magnets fluctuating, can make very nice p-bits. Okay, so these are all recent developments. I'm just showing you this just to get to the point that this is a very active field that with a lot of interest from a lot of people. Okay, but something might be bothering you, which is I've been talking about a 2-terminal resistor, but how does that become a p-bit that I showed in the beginning? Now, to understand that, you have to look at this technology called spin transfer torque MRAM, and this has been scaled up to these enormous densities. People have put 1 billion MTJs in these chips, and they have this 1 transistor, 1 MTJ technology. Okay, this is the architecture. And there are a lot of people doing this, Everspin, Samsung, Global Foundries, Intel, and many others I probably forget. But what you do is you make 2 changes to this structure. You say, I'm going to change first of all, I'm going to change the magnet, obviously, that I'm going to make the magnet an unstable magnet. And I've made a terrible memory because it is now fluctuating as a function of time. If you put anything on this object, it forgets its state possibly in the next nanosecond or so. And then you put 2 more transistors. This inverter sign can sometimes make people think of different things like an op-amp. No, you put 2 more transistors. So overall, this circuit now is 3 transistors and 1 MTJ. And if you look at the behavior of this model using these sort of state-of-the-art device models in SPICE, and you solve the magnet equations with transistor models and so on, is a function of this input voltage of the transistor. You see this behavior that, this is the V out, this is the V in. You see this sort of tunable randomness that I've been showing you, which is exactly, well, which is not exactly, but which is quite approximately like this behavioral equation that we've been talking about. Now we can get into the details of how this circuit works and why it shows you this tunable fluctuation, but the essence is that in the end, you've received this functionality of randomness, true randomness, with only three transistors and one MTJ. And as I'll show you later, that's actually very significant. Now, we've built this with our collaborators from Tohoku University. They sent us these stochastic MTJs that I showed you earlier, and essentially in the same circuit setup, but we've put some source resistances, controlling variations, and we've put a slightly more powerful, amplifier. But essentially, it's the same idea. And we've got this tunable analog randomness as a function of time. And as I said, these magnets were slow, and this was a tabletop experiment. So that's why what you're seeing is this millisecond operation. And this is our chip where we have, this is a PCB with 8 such MTJs. And this is exactly the same architecture that I showed you in the beginning, that you have these 8 MTJs, they're talking through a synapse, their outputs are collected, and the inputs go back to the qubits. So what can you do with this? Well, we've solved the factorization problem with this integer factorization, which I briefly mentioned earlier. Now, this choice was really motivated by the field of quantum computing. In quantum computing, people expressed factorization problem as an optimization problem a long time ago, and we saw that we could implement that same algorithm. And well, how does this work? Well, it's actually very simple. You'll see it in a second. So what you say is something like, okay, let me have an energy function E, and let me have the factor F that I'm trying to factor. And if X and Y are the factors I'm looking for, and I'm assuming that F is some composite number like 21 or something, then you're trying to find the factors of 21. And you say that, okay, X and Y are the things that I'm trying to find, and XY minus F, if I square that quantity, that's going to be 0 only when these XY actually multiplies to F. Okay, so that will be an energy minimum if you satisfy this relationship. And this is a very simple idea, and people have solved this with these adiabatic quantum algorithms and so on. But all you have to do next is to express X and Y as binary numbers so that you can write large numbers. And then your P circuit will naturally minimize this energy. So for the P circuit to naturally minimize this energy, what you have to do is you have to find the synapse, which is this interconnection matrix. That's a one-time process where you take the derivative of the energy. It's a one-time efficient process that is done, and it's being programmed to your synapse. But then the circuit actually will minimize that energy naturally. You don't have to do anything extra to this. And as in any experiment, of course, you need some sort of calibration. And what we did was we first uncorrelated all the p bits, and then we let this thing evolve as a function of time. And these are the X and Y in the X-axis. What you're seeing are the different factors that this can be. And this is a time averaged measurement that you're seeing here. This is sort of like 10-second or 20-second averages. So you're seeing when they're uncorrelated, you try to make it a nice green flat grass so that everything comes up with the same probability, because this is the uncorrelated stuff. And when you correlate it, this now works like an integer factorizer. Okay, that's okay. We can factor something like 945, and if you take a 10-second average, the system shows the correct factor with highest probability. Now, factorization is a tricky example because, as you know, it has applications in cryptography. People have efficient quantum algorithms, the famous celebrated Shor's algorithm for it. So we're not trying to or claiming that this is going to solve factoring. This is just an energy minimizer in hardware, and it does it on its own, and it could minimize all sorts of other problems that may not have efficient algorithms like the Shor. Okay, so that's basically the proof of concept of this idea. Now, there are more sophisticated ways of solving the factorization problem that can take you much further. Again, it doesn't solve the crypto problem, but it can take you much further, and it illustrates other things. Now, this is this invertible multiplier that I mentioned to you earlier, where you have a multiplier. This is the schoolbook multiplication algorithm. You have these AND gates and full adders, and you have, you know, this just multiply. The AND gates are the bitwise multipliers, and then the full adders sort of add these layer by layer, and you add everything up, and this is like a 8-bit multiplier that multiplies two 4-bit numbers. Now, with p-bits, though, what you can do is you can fix the output and ask the question, can you give me the inputs for this problem? And this is actually a satisfiability problem. That this is very important in computer science, to be able to ask this question, that what makes this output of this circuit 1? Or what makes this output of this circuit, let's say 143? Give me the factors for that. This is a very general problem, but the key insight here is that you can do this with literally in hardware. You can use your VLSI techniques, but then build this invertible circuit and run it in reverse. And just to show you some of the recent unpublished results that we have on this, this is a pretty large number. Now, it's not like 21. I don't think anyone can quickly factor that number. This is a 32-bit number in the billions. And this is how the P circuit finds the factors as a function of time. You run this, you anneal this as a function of time, and the P circuit sort of gives you the correct factors. And just to get you, calibrated, this is done in a 2200 p-bit network. So these are getting quite large now compared to the 8 that we did. And this is 32-bit factoring, and this is very large compared to everyone else. This actually is very competitive in terms of Ising machines. I don't think anyone can go this high in factoring, because factoring in classical computers is such a hard problem that it gets out of hand very, very quickly. And the key point, again, is not that this is a great factorizer or this is better than this or that. The point is, this is right now taking milliseconds to solution. We have efficient FPGA designs. And the point is, if you do it with MRAMs, where your MTJs are flipping every nanosecond rather than these heavily penalized clock frequencies and digital emulators, this can be nanoseconds. This can be orders of magnitude more than what you can do with these things. And just to drive that point home, there is a competition called SAT, the satisfiability solvers. They take these very difficult satisfiability problems and they use their best heuristics and best tools in software, and they make these yearly competitions every year. And these are 3 solvers from last year's winning the SAT competition. These are, I think, KissSat is the names don't matter. They are very creative with their software algorithms. But KissSat, I think, was last year's winner. Crypto Minisat, Lingaling, etc. But our FPGA, you can see that when you do this invertible logic, which literally takes the SAT problem to the hardware domain, even with an FPGA, you can get 2 orders of magnitude improvement on solving these important industrially relevant problems. Okay, and again, the real point I'm trying to make is, if you take it to the MTJ, there can be orders and orders of magnitude improvements over this improvement. So that's the sort of classical optimization and so on. Let me say, maybe this is interesting to some of you, that let me say a little bit more about this connection between p-bits and qubits, because sometimes people ask, okay, this is very good, but why do you call it a p-bit? Why do you say that it is not just a stochastic bit or something? Sometimes people come back with this thought. And the answer is because we've always been interested in the connection to qubits. I mean, we were never really trying to solve SAT or improve a optimization problem. We were really motivated by an understanding of qubits. And it turned out this understanding led us to this finely balanced idea that, okay, there are some systems where you can take a qubit array, like let's say I'm saying d-dimensional here, but read it as 2. This is just 2-dimensional. You can take a 2-dimensional array and you can make it, you can make replicas and it becomes, in a sense, three-dimensional. And you can represent these qubits with p-bits. Now, this is only, remember, again, I can't, emphasize this enough, that this only works for a subclass of quantum systems that are called sign problem free. Now, again, this is a deep discussion in and of itself, so I'm not going to have time to go into that, but it just should tell you that, for example, the Google problem, the Google Santa Barbara collaboration that happened recently would, as you guessed it, would be a sign problem full problem that we couldn't emulate it with p-bits. In fact, you could emulate it with p-bits, but then you need to run it for a very, very long time, which is the claim, which is the exact same claim that they are making, that it would take thousands of years to solve that same problem with p-bits. But the D-wave problem and many other problems are sign problem free. And just to show you a striking example, the details are not very important, but this is a problem where you're solving this transverse field Ising model. It's a prototypical quantum model that's a model of ferromagnetism, and it's very simple. Okay, we're looking at the Z spin. Z is out of the page here. We're applying an X-directed magnetic field. X is into the page. What happens if you apply an X-directed magnetic field to a Z-directed magnet? Well, the Z component dies down. So that's what the quantum Boltzmann law is showing you. I mean, this is, of course, a simple example, but remember, in general, to do this for a 10-qubit problem, you need to work with a 2 to the 10 by 2 to the 10 matrix. To do this for a 100-qubit problem, you need to work with a 2 to the 100 by 2 to the 100 matrix. So this is, I mean, it can look easy, but quantum will get out of hand pretty quickly. So we solved that. This is a small example, so we could solve that exponential problem here. I think this is a 8-qubit problem that we're solving. And then we solve the same problem with these replicated p-bits, okay? And with these replicated p-bits, we saw that we get these red dots, that these are probabilistic samples, of course, because the probabilistic computer. But as you take more and more samples, as you take like 100 samples or so, you land right on top of the exact quantum solution. So this sort of tells you that, hey, look, here's a case where you can do this efficiently and quickly, and you're solving some quantum problem. And there's actually more, because it turns out the D-Wave has been working on this field for many years. So they've looked at this algorithm of simulated the quantum annealing algorithm in their machines from every which way. And they've discovered that actually this is a great algorithm if you use it in software as well, that if you use this replica idea that I mentioned existed, if you do it and if you try to use this algorithm to simulate these quantum systems, what D-Wave is doing, this is a very good algorithm. But the point is, it's very expensive. That for a 100-qubit problem, you need you add 10 more replicas, it becomes a 1,000-qubit problem. So in software, it's very expensive. But the point is, if you do it in hardware, then you may not be subject to the same requirements. Okay, and we've implemented this in FPGAs. We can go up to 250 qubits, etc. But again, the real point I'm trying to make, the essence of everything I'm trying to say is, if you do it with NTJs or with a scalable fabric, you can take a 2,000 or 5,000 or 10,000 qubit problem and make it a 1 million qubit problem. Now, D-Wave gets a lot of criticism. You may have heard this before, but if you take, it still is a quantum computer in some sense, and they still solve a lot of things competitively. And if you take a 2,000 qubit and make it a 1 million qubit computer, that can get very exciting. Okay, and the number 1 million comes from this basic idea that, okay, let's say we have 1 gigabit p-bits, and let's say 1,000 replica, 1,000 p-bits per qubit, and that gets you to these enormous scales. Now, let me get to the final part here as I'm nearing the end. So why is this better than what we can do? Now, unlike quantum computers, we need a more refined answer here. We can't just say that we can solve this problem or that problem better than any classical computer, because you can always say, you know what, I'm going to use random number generators and I'm going to do what you're doing with your p-bit, which is a fair criticism and which is absolutely true. We are ourselves using FPGAs and CMOS chips to sort of emulate this system. But as I've learned more about FPGA and ASIC design, my respect to the MTJ-based p-bit increased enormously because of the following reason. Okay, so this is the behavior we want. We want this p-bit as an analog input digital output object, and I need intrinsic randomness in there. So how do I get there? Now in CMOS, some of you might be familiar with this. The circuit looks complicated. It isn't. It is this linear feedback shift register circuit, which is a bunch of flip-flops that go from 1 to 30. Okay, it's a flip-flop circuit, and you feed the output back to itself. It's basically a circular shift register. But then, if you XOR some of the outputs and before you feed it back to this LFSR, this tends to generate random-looking signals. And for deep reasons, a simple operation like XOR produces a lot of random looking signals. Okay, it's actually remarkable. So you can get something like a pseudo-random number generator that repeats itself as a function of time, because it'll do exactly the same thing, but it'll be very random looking, and it'll pass actually certain randomness tests and so on. Now, so the way to make a CMOS p-bit, then you need, of course, the biggest part is the random number generator. And then you need your activation function for the hyperbolic tangent. You need a comparator for the sine operation. We said, you know what? Let's not even worry about the hyperbolic tangent or the comparator. Just focus on the random number generator. So we've hand designed this LFSR, starting from a single transistor. And those of you who are familiar with synthesis and computer architecture will understand the difference between giving it to Verilog and doing it, transistor by hand. So we did the best we could to reduce the number of transistors in this LFSR. It took to 1200 or 1194 transistors just to get a 32-bit LFSR, while in this MTJ, we have 3 transistors and 1 MTJ, which is roughly like, let's say, 4 transistors or so. The area is remarkably small. And of course, when you have more silicon area, your energy per random bit also increases. And we saw at least an order of magnitude improvement in the, a penalty in the FPGA case, not FPGA, in the LFSR case. And we think, this is actually not even a serious comparison, because we didn't take into account the activation function, the comparator, parasitics, clock power, interconnects. When we show it to circuit designers, they shudder, because we want million LFSR, we want million p-bits, not just one. Now, there's actually another serious point that why such small objects can be so important. And this is, again, you understand the seriousness of the issue once you start working on this. The LFSR I mentioned, this 32-bit LFSR, right? It's got a very large period. It repeats itself every 8 billion cycles or so. And you're like, okay, 8 billion random numbers. That's a lot of random numbers. Why do I need a true random number? Well, the problem is you remember that this LFSR is clocked at 125 megahertz or 200 megahertz. And if you clock this at 125 megahertz, you repeat every random number every 30 seconds, because 125 megahertz goes through 8 billion pretty quickly. Okay, so this is actually a very serious problem, and you don't want the same random number because of these sneaky correlations and things like that. It really kills everything you're doing in Monte Carlo and optimization. So this is why we think that in terms of hardware, this p-bit at the device level looks very good. But there's a larger point, and that ties back to one of the first things I said. And there's an architecture sort of idea that's very important here. Now, in order to appreciate that I'm showing the same architecture, it's always the same architecture as you're seeing, that there's n p-bits that are being routed back and they talk to one another and so on. So what is the key metric for such a computer? For example, in digital computers, we often talk about clock speeds, right? We say something like, okay, my CPU was running at 500 megahertz 10 years ago. Now they're running at 1 gigahertz. People are trying to make it 3, and so that's one serious metric, important metric in computer architecture for classical computers. So for probabilistic computers, there's a similar metric, which is this flips per second. Now, what is flips per second? In other words, it's samples per second. How many, you're in a probabilistic space, how many samples can you get? How many independent samples can you give me every second so that I can get to a useful answer as a function of time? And if I increase this number of flips per second, I'll obviously get to the answer quickly. If I need 1 million flips, for example, I'll get there quickly if I'm fluctuating much faster. Now, I put this thing in parentheses there. I've said informed flips. Now, this is important because one of the caveats I said in the beginning is that this synapse, the feedback needs to be fast. Now, what happens if the feedback is not fast? Well, then you're looking at everybody's shouting. Nobody's listening to each other. Everybody's shouting, and you have a lot of flips per second. There's a lot of noise, but it's not going anywhere. So I just put that informed in there to say that you can't just take 1 million computers and get random numbers and beat this P computer. No, it has to be integrated, and it has to be smart, and it has to listen to one another, okay? And that's where all the difficulty comes in, actually. So the next easy question, I guess, that some of you might be asking is, okay, fair enough. How many flips do I need? Well, that's a complicated question because it depends on your problem and it depends on the algorithm you're running. And in general, if you talk to a computer scientist, the theoretical computer science community will say, forget the prefactors. Just tell me the algorithmic scalability of the problem, that this f of n, like if I double the size of this problem, what happens to your time? And it's a very powerful way of thinking about complexity, because then you don't have to worry about where you're running, whether you're running it on your laptop, on my laptop, on the P computer, or whatever. So this is a powerful way of thinking. But in real life, we need prefactors. In real life, it makes a big difference for us that if you solve something in a second or in a microsecond. Okay, so that's where the pivot comes in. We make the argument that yes, you can solve all of these problems in classical computers, but you're going to take a huge prefactor hit if you do it with these expensive random number generators and so forth. Now, just to calibrate you with state-of-the-art, that these are published numbers that I can easily, if you're interested, I can show you references. State-of-the-art GPUs and TPUs. Of course, people are, as you know, people are interested in probabilistic accelerators, probabilistic samplers everywhere. I mean, in machine learning, AI, Monte Carlo, this is not a problem that we're interested in solving. And the best frequency, the best flips per second these days are around, with GPUs and TPUs, are around 10 flips per nanosecond. Now, just wait for a second and appreciate what that number is, because I just mentioned the clock frequencies are around, a gigahertz or so in digital computers. So you're making this complicated flip operation with all its complications 10 times a clock cycle. So let me tell you that this doesn't come easily, that if you check these papers, they're very smart people trying to do very high levels of parallelism and so on. So that's the state of the art, 10 flips per nanosecond. Now, if you have 1 million p-bits, which is well within the MRAM technology, each flipping every nanosecond, which is experimentally demonstrated by 2 different groups now, then you can get 10 to the 6 flips per nanosecond. Okay, this 1 million flips per nanosecond. So it's a 5 order of magnitude improvement in these very important problems. And let me just tell you that with FPGAs, with these nano-inspired, physics-inspired architectures that we envision for the MTJ, we're around 100 flips per nanosecond, but it is not going to be 1 million anytime soon. It's just, you just run out of silicon, you just run out of resources. Now, another question one might ask is, okay, but why not 1 billion? I mean, since this is all massively parallel, can you solve this with 1 billion p-bits, because that's going to be even better. And it's within the technology, because there's this proven manufacturability of the STT-MRAM technology. We're not talking about some exotic device here. This is real. So the problem is if you talk to, if you go to the details and talk to these ASIC designers or people who integrate these things, you're probably going to run into some power wall, area wall, or interconnect wall before you can fit that many, because we're not just doing a very regular memory structure. We have all this interconnects that we have to worry about. But 1 million is actually, this 1 million is a well thought number in terms of power and whatnot. So this is my last slide here. I hope I'm a little bit over time. I hope not too much. So I've talked to you about this machine learning and NISQ era quantum computing related applications with, with p-bits and p-circuits. And I've talked about these different ways of implementing p-bits that you can have, FPGA, CMOS, MRAM, or even emerging nano devices. So these are all, we're looking into all of these possibilities. The jury is out. And there's this possibility or prospect of beating classical computers. So getting to this probabilistic advantage, probabilistic supremacy regime, which is can be orders of magnitude better than what you can do with today's technology. And finally, what problems should we think about? What problems would benefit from this? As I mentioned, this is domain specific, but you should look for naturally stochastic problems, okay? Because that's where the p-bits really shine. And the point is machine learning and optimization are full of these examples. With that, I will conclude, and I thank you very much for your attention.
Thank you so much, Kerem, for this wonderful overview. I mean, I'm not an expert in this field, but I have to say that I really enjoyed your lecture. So on behalf of our team and participants, I clap.
Thank you. Thank you very much.
Nice, lecture. So maybe I can get this started while some people will write or raise hands. So basically the p-bit computing. So okay, you are putting some transistors and you are making the probability, in a more controlled and faster way. But how the MTJ itself, contributes to the whole thing. So the dimension of the MTJ or the intrinsic resistance of the, I'm talking about the TMR of the MTJ. So how that contributes to the whole thing. So could you shed some lights on that?
Yes. So this is, let me go back to that. I skipped, as you correctly caught me, Shubhankar, I skipped a whole lot of details on how you get this how you get this behavior. How does it look? How does it correspond to one another? So you're absolutely right that the TMR is a very important metric here, because TMR sort of will make this random region cleaner and cleaner. Right now, you can see that it is not always rail to rail, for example. If we had a slightly higher TMR, it would look even more and more binary. So TMR is an important metric. Now, this doesn't assume heroic TMRs. This TMR, by the way, for everyone's reference, is the ratio of the anti-parallel resistance to the parallel resistance. It's some metric that measures that ratio. And we didn't use heroic TMRs here, meaning I think this particular plot uses maybe 110%, 115%. So it gives you, I think the good thing about the MTJ is it takes the same thermal noise, but it turns it into something much bigger because of this TMR, because of this big resistance change that you suddenly become, 10 kiloohms becomes 20 kiloohms. Now, so TMR is very important. That's number one. And the second thing you mentioned was, how about resistance matching? That these objects have their own resistances. It won't work for any resistance, which is absolutely correct. That to get this symmetric sigmoidal behavior, you need the transistor resistance to be sort of matched to the MTJ resistance. And what that means is now you have to control your array product or your diameter of the MTJ and carefully align it. Now, luckily, the right resistance ratio, they are close already, because these small MTJs have kiloohms of resistance, or in fact, hundreds of kiloohms. And these transistors, when they're barely on in this middle region, they also have tens of kiloohms. So these are not orders of magnitude different. So we're lucky there. But there are many other details that you have to reckon with with like in-plane magnets, circular magnets, elliptical magnets, how to design the stochasticity, how do you maximize this thing? And these are things that I didn't get into, but these are very important points. And yeah. Okay,
thank you so much. So there are a few questions, but I have to just tell that there are also some compliments from Professor Rao.
Okay.
Then he says excellent talk, and Professor S.D. Mohanty, who is from Michigan State University. He is associated to NICER actually. So thanks, Professor Mohanty, for joining the talk. So I get the question of Aditya Singh. So he said, thank you for such an interesting talk. It was mentioned that the p-bit structure is clockless. However, the solution of factorization problem seems time dependent. So if we want to build a prime factorization algorithm using p-bits, isn't it gets even more important to have a clock system?
Very good point. So Aditya, the fact that this clockless doesn't mean it's not time dependent, right? I mean, clockless just means that it's going to self-organize, like a, water flowing through a waterfall or something. It's still be time dependent. So being clockless doesn't necessarily mean it doesn't depend on time. Now, if you want to do a prime factorization algorithm, the final point is the buck stops where you want to solve it quickly. So with clocks, there are fundamental serialness problems that let's say all of us are going to say something. I have to speak, and then Shubhankar speaks, and then I speak. So clock sort of arranges that. With p-bits, you don't need that. While everybody is not shouting, it can be, a lot of people can speak at the same time and get you to the right conclusion or to a good place, to consensus. So this is the best way I can quickly explain it. But we can discuss that in detail as well.
Okay, thank you. So the next is Kelvin Fong. So you please unmute and ask your question.
Hey, hi, Kerem. How are you? Long time no hear.
Hi, Calvin. Yeah, Calvin and I, we know each other from a long time ago. How are you?
We go way back.
Way back, yes.
Yes. So thanks for a nice talk, right? Let's actually have a couple of questions. I think the first one is, we've been looking at this MTJ-based random number generators for a long time, right? So I think one of the things that has always troubled me is that if you look at this lower energy barrier, right? What happens is you really kind of skew the retention of the MTJ, and then as you try to sense it, right, you actually kind of bias the probability of sensing the state. So how do you overcome that problem, or is that not a big problem at all?
Right. No, it's an excellent question. The question Calvin is asking is there's a fundamental problem in memory that if you make something easy to read, you're also, if you make something easy to write, then you're also making it easy to disturb, because if it's easy to write, it's going to be easy to disturb by noise. But in MTJs, this isn't necessarily true because you have to look into the details. And the detail is this, that when you have in-plane magnetic tunnel junctions, that some of these recent developments, here I'm showing a perpendicular MTJ, but if you look at an in-plane or a circular MTJ, it becomes enormously difficult for spin transfer torque to bias it. This is the same reason why in-plane magnets are harder to switch, because of the strong DMAG field. When you push current to this in-plane magnetic tunnel junction, if you have an in-plane circular or in-plane elliptical magnet, it becomes very hard to disturb using electrical means, while because the barrier is low, it is very susceptible to thermal noise. So you have an ideal object that's fluctuating as a function of time because of noise, because noise enters like a magnetic field. So it's very weak to magnetic field, but it's very strong to spin current. And this is sort of a fortuitous thing in this case, because you can push a significant amount of current and still you can't pin this. This isn't necessarily true for PMAs though. PMAs, as you said, are easier to pin. But even in that case, there are dipolar fields that you want to cancel to begin with. So actually in the experiment we did, this worked out nicely, that there was a dipolar field and the spin torque, instead of biasing it, it made it more random. So I think it depends on the details, but we have to talk about the details. Yeah, yeah.
Right, right. So then the second question that I have relates to the architecture aspects. When you look at the kinds of problems you're mapping to the PBIT, right? So what are the kinds of resource requirements that goes along with the scaling that you're talking about? Because we've been starting to look at some Ising machines and stuff like that, right? And it turns out that if you want to perform the updates and stuff like that, you might have a growing memory problem, right? Because the number of memories that you can track starts to grow exponentially with the problem size.
Right. So I don't know if it grows, at least in my experience, I don't know if anything I don't know that synapse or the memory grows exponentially or not. But if you do all to all, for example, in a 2200 qubit problem that we put to these FPGAs, if everyone needs to talk to everyone else, that grows as n squared, right? You have a big problem. You're going to have 4 million connections. Now, our solution to this is to keep the matrices sparse. From the get-go, we say that whatever Ising graph or whatever probabilistic problem or AI problem you're solving, we cannot tolerate very dense graphs. What that means is you can have 5 neighbors at most or 10 neighbors at most. And we have ways of sparsifying dense graphs that you can take, for example, factorization, this 2200 is an example of that. If you just put it as an invertible multiplier, it has some nodes have 50 neighbors, but then you can't deal with that. So you take that architecture, you come up with a new graph such that everyone has 5 neighbors. So everything, all the claims I make about scaling up is really based on the assumption that these graphs will be sparse. Otherwise, I completely agree with you that the resources will kill you.
But even if you do that, the number of p-bits that you need would also grow, right?
Yes,
but does it grow? Right, but does it grow linearly? So did you get an advantage doing that?
Yeah, I mean, I don't know if it grows linearly, but it certainly doesn't grow exponentially. But I mean, it grows polynomially. But to me, p-bits are cheap. I mean, what's expensive is the communication. Because p-bits can be upwards of millions. Whereas communication, there is no easy way to scale. So there is this fundamental thing that this is a discussion in VLSI, as you know very well, that which one, if you had the chance, what would you do? Would you put more transistors to release your interconnect? And that's really the same thing here. And yes, it really grows. I mean, this 2200 p-bits could solve much bigger problems, but we pay the price to sparsify it as it grows polynomially. And with a scalable technology like MTJ, we think, yes, there is still a lot of room for advantage, but the ultimate scale, of course, I don't know.
Okay, cool. All right, thanks very much. That's all I have.
Very nice. Thanks for all these excellent questions.
So the next question is by Abhishek Misra. So he's asking, can the p-bits be implemented to realize the system with in-plane and out-of-plane magnetic anisotropy?
Can the p-bits implemented to realize this is an in-plane? Yes. So as I was talking to Calvin, we have two. I mean, I know of now multiple experiments that the experiment I showed you from this this optimization problem was out-of-plane anisotropy, and that can work. But as Calvin indicated, that those can be easier to disturb. But then if there is dipolar coupling, it can be a good thing, etc. So it becomes tricky, but it's possible. With in-plane magnets, the situation is clearer, that it's extremely hard to disturb in-plane magnets with spin currents. So yes, the answer is you can have in-plane and out-of-plane magnetic anisotropy for p-bits. Just one final thought, and that is in-plane magnets tend to be faster because of this high Dmag field. Again, if you know, I don't know how much you want to know about the magnet physics, but in-plane magnets tend to fluctuate much faster, which we can discuss.
Okay, thank you. The next question is by another Abhishek Sharma. Thanks for the talk. What about the effect of temperature distribution in the p-bit chip?
Yeah, it's a good question. I think Abhishek is hinting at the idea that, okay, you have an object that's fluctuating as a function of temperature. but then what if I change the temperature? I mean, how is that going to affect things? Abhishek, the thing is, when these are very low barrier magnets, the temperature dependence goes down, because think of the exponential. It's exponential x, a delta over kT. When delta is large, like 15 kT, even a small change in the temperature is going to lead to very large changes in your retention time. But when your delta is very small, e to the x is like x. So your temperature dependence is, I mean, e to the x is like 1 plus x. So your temperature dependence isn't so important anymore. So the lower the barrier, the better it is. Very good question.
All right, thanks. I think the next question is by Marco Hoffman. Marco, would you like to ask, or I should read it? Okay, I read it. So he's asking, thanks for the great talk. I'm not very familiar with the complex factorization problems, so I may have rather basic question only slightly related to the p bits. What if multiple solutions with integer numbers, that is 4 into 5, 20 equal to 2 into 10, exist to a factorization problem? What determines which solution is found, or could it find even a function or collection of some all possible solutions?
Very good question, Marco. It is, it's an excellent question. These are degenerate solutions, and some of them exist in the system and some of them don't. For example, 4, 5 and 5, 4 are degenerate solutions, and complete random noise determines which one you're going to go to. Okay, you can see 4 times 5 or 5 times 4, and these are always going to be degenerate like that. But the other point is, you indicated, for example, 2 times 10, and I could raise you and I could say, what about 1 times 20? That's also a solution. But some of these degenerate solutions cannot be written in terms of your problem, because you have only 8 bits to write. For example, if you have 4 bits to write your input, you can express 4 in binary, but you can't express 20 in 4 bits. So those are automatically out. But the larger answer to your question is yes, these are all degenerate solutions, and complete random noise determines which degenerate solution you're going to land, because the system just really cannot distinguish 4 times 5 and 5 times 4. I hope that sort of explains.
Okay, he thanks you. So thank you very much. I think we have no more questions.
Okay.
So we like to just give a small token of appreciation. Could you kindly stop sharing so that I can share my screen?
Yes, of course, of course.
Okay. All right. All right. So do you see my screen, Kerem?
Yes, I can see it. Yes.
All right. So I think on behalf of our team and the participants, so we'd like to thank you by presenting this small digital plaque. So W2S seminar, webinar series on spintronics, National Institute of Science, Education and Research, NISER Bhubaneswar, India, takes pleasure in presenting this plaque to Professor Kerem Camsari from UC Santa Barbara, USA, in recognition and appreciation for being a very valuable speaker to give a lecture on scalable probabilistic computing with magnetic tunnel junction. So again, many thanks, and I really appreciate your time and efforts so early in the morning. So thank you very much, and I hope to see you in other talks as well. You are most welcome to attend.
It's been a great pleasure.
Yeah, thank you. And next week we have a talk by Professor Karin Emerson from University of Duisburg in Germany. And I hope you guys please stay safe and see you next week. So thank you very much. Have a nice day, Kerem. So
thank you.
Thank you so much.
Thank you
so much all. Bye. Good night.
Bye.
Or good, have a nice day. Bye.